For almost all of human history, the sun was something our bodies lived beneath, not something our civilization depended on surviving. Then, in 1859, a solar storm sent electrical currents through telegraph lines, disrupted communications, and filled skies far from the poles with auroras. Our ancestors could lose every machine they owned and still continue. We have built a world where that is no longer true. So what did the Carrington Event really do, and what would a comparable solar storm mean for the modern world? For almost the whole span of human existence, the sun was powerful without being connected to civilization. It warmed the ground, shaped seasons, influenced rainfall, guided migration, and helped determine where plants could grow and animals could survive. Human bodies evolved under its daily rhythm, waking in light and resting in darkness long before anyone understood what the sun was. Yet for our distant ancestors, even a violent disturbance on the sun had very few direct paths into the tools they depended on. A hunter moving across open grassland, a family tending a small fire, or a farming community storing grain did not rely on transformers, satellites, radio signals, or long electrical conductors. Their lives could be threatened by drought, cold, disease, storms, crop failure, or conflict. But the machinery of society itself was not electrically connected to the sky. This distinction matters because the danger discussed in the story of the Carrington Event is not simply that the sun can become active. The sun has always been active. The deeper change happened on Earth, when human beings slowly built systems capable of responding to disturbances far beyond the atmosphere. For early humans, survival depended on local knowledge held in bodies, landscapes, tools, and relationships. Fire had to be carried or remade. Food had to be found, hunted, gathered, grown, or stored. Messages moved only as fast as a person, an animal, a boat, or eventually a written document could travel. A disruption in one valley did not instantly interfere with life across another continent. Civilization grew more complex over thousands of years, but for most of that time its essential functions still remained separated by distance. The sun could alter climate over long periods, and its light governed the biological world, yet there was no planetary network of metal waiting to carry induced electrical currents from one place to another. Even when cities became large, empires connected distant territories, and trade crossed seas, most human systems were still mechanical, biological, or chemical rather than electrical. Water flowed through channels, grain moved in carts, ships followed winds, armies marched, news travelled through riders and messengers. The first humans who left Africa could never have imagined a civilization in which an invisible disturbance around Earth might affect navigation, communication, finance, transportation, and power at the same time. That does not mean earlier people were safer in general. Their lives were often more exposed to hunger, injury, infection, weather, and local environmental change. It means only that one particular kind of vulnerability had not yet been created. As human societies learned to control more forms of energy, they gained extraordinary abilities. But each new system also created new dependencies. Metal tools changed agriculture, writing changed administration, roads changed movement, steam power changed industry. None of these, however, made the functioning of an entire society immediately sensitive to changes in Earth's magnetic environment. That threshold came much later. The important shift was not a sudden weakening of humanity, but a transformation in what civilization required in order to continue operating normally. Today, electricity is so familiar that it often disappears from attention. A light turns on, a signal reaches a phone, a payment moves through a network, and a satellite silently provides timing or position. These actions feel ordinary because the systems behind them usually work, but they are the result of a very recent layer placed over an ancient human life. Beneath it remains the same species that once navigated by landmarks, stars, memory, and shared knowledge. Above it now stands a technical world linked by conductors, electronics, and signals. The Carrington Event becomes meaningful only when these two histories are placed beside each other. The ancient history of humans living beneath an active sun, and the much shorter history of humans building machines that can respond to it. Long before 1859, the sun was already capable of violent change. What had changed was us. Long before electricity became ordinary, Human societies had already learned how to build cities, move food over great distances, organize armies, maintain governments, and exchange information across large territories. None of this was simple, and none of it was free from failure. Roads could wash away, crops could fail, ships could sink, messengers could disappear, and entire regions could become isolated by war or weather. Yet most essential systems still operated through forms of energy that were visible and local. People burned wood, charcoal, oil, or coal. Animals pulled carts. Wind moved ships. Flowing water turned wheels. Human muscles lifted, carried, dug, and built. A failure in one place could be severe, but it usually did not travel through an invisible electrical network into distant communities within moments. This was the world in which nearly all recorded human history unfolded. Even the largest ancient and medieval states depended on physical movement. Grain had to be stored and transported along roads or rivers. Orders from rulers had to be written, carried, read, and sometimes copied again. News crossed mountains at the pace of horses and seas at the pace of sails. Time itself was experienced locally. A town could organize its day by sunlight, bells, or mechanical clocks without needing a signal from a satellite or electronic network. These systems could be slow and fragile in their own ways, but they were not synchronized by electricity. That difference matters when we think about the Sunday. A strong solar disturbance could occur above a world filled with farms, ports, markets, workshops, and armies, while leaving most of those systems without a direct electrical pathway through which the disturbance could enter. Human beings were still exposed to the natural world, but the connection was mainly through climate, weather, light, heat, and the biological conditions that support food and life. The deeper history of our species makes the contrast clearer. For countless generations, human survival depended on small groups reading landscapes, remembering water sources, recognizing seasons, maintaining social ties, and passing practical knowledge from one generation to another. Later civilizations added roads, writing, taxation, ships, mills, and increasingly complex institutions. Each development increased coordination across space, but coordination was still limited by the movement of matter and people. A message could not instantly cross an ocean. A distant machine could not fail because a current had been induced in a connected network thousands of kilometers away. There was no electrical grid to protect, no radio spectrum to disturb, no orbiting navigation system to degrade. This does not mean pre-industrial civilization was resilient to every shock. It was often highly vulnerable to famine, epidemic disease, military conquest, and environmental stress. The point is narrower. Its vulnerabilities belong to a different technological world. By the early 19th century, however, that world was beginning to change. Experiments with electricity and magnetism were revealing forces that people could not see directly, but could learn to measure and use with increasing precision. The relationship between electricity and magnetism was becoming a subject of scientific study. At the same time, industrial societies were finding ways to move people, goods, and information faster than before. Steam power reduced some old limits of muscle and wind. Railways began to compress distance. Then communication itself started to separate from physical travel. For the first time, a message could move through a wire far faster than a horse, ship, or train carrying a written page. That transition was profound because it created a new physical connection between distant places. Human civilization was beginning to build long, conductive paths across the ground, and those paths could respond to forces their builders did not fully understand. The world had not yet become electrically dependent, but a threshold had been crossed. The sun was still the same active star that had risen over every human generation. What was changing was the architecture of human connection beneath it. By the middle of the 19th century, human beings had begun to build something new beneath the same sky that had watched over every earlier generation. Telegraph wires stretched between towns, cities, railway stations, ports, and government offices, carrying coded electrical signals across distances that had once required days of travel. The change was not simply that messages moved faster. It was that communication itself had become dependent on long metal conductors connected across the landscape. For the first time, a disturbance in the electrical environment around Earth could find a direct physical pathway into one element of civilization's working systems. This was a profound departure from the world in which for most of our species' history, information was stored in memory, gesture, speech, markings, and eventually writing. Knowledge moved with bodies and objects. A spoken warning could travel only as far as a voice, and a written message only as fast as someone could carry it. Telegraphy broke that old relationship between information and physical travel. An operator could send a coded signal through a wire, and another operator far away could receive it almost immediately by the standards of the time. Governments, merchants, newspapers, and railway systems found value in this new speed, yet the network was still primitive compared with what would come later. There were no satellites, no digital computers, no electrical grids supplying entire regions, and no global positioning systems. The telegraph was only an early layer of electrical dependence, but it was enough to create a new kind of vulnerability. Long wires were not isolated from the planet around them. Electrical currents could be influenced by changes in Earth's magnetic environment, even when the people using those wires did not yet understand the full chain of causes connecting the sun, space, and the ground beneath their feet. That is the essential threshold. Humanity had not suddenly become weaker. It had become more connected through a force that could also respond to natural processes far beyond ordinary weather. The same species that had once carried messages along trails was beginning to place some of its communication system inside an electrical relationship with the planet itself. The shift was easy to miss because, in daily life, the telegraph appeared to be a triumph over distance. A wire joined two places, a signal crossed it, a message arrived. Nothing about that routine suggested that events on the sun might one day interfere with the exchange. The danger was not visible in the wire, just as a modern user cannot see the entire infrastructure behind a phone call or a digital payment. Dependence often grows quietly because successful technology becomes ordinary. As more wires were built, the network became more useful, and usefulness encouraged further expansion. This pattern would repeat many times in the future. Electrical power, radio, satellites, computer networks, and precision timing would each make civilization more capable while also tying important functions to systems that could be disturbed in ways earlier societies never faced. The telegraph was the beginning of that long transition. By 1859, humanity still lived in a world of horses, steam engines, handwritten records, and mechanical tools, but its nervous system had already become electrical. That small change was enough to matter. When a powerful disturbance reached Earth that year, it did not need to destroy cities or overturn governments to reveal something new. It only had to enter the wires. For the first time in human history, activity far above the atmosphere could reach directly into a communication network built by human hands. The significance was therefore larger than the equipment itself. A telegraph line was not merely a faster messenger. It was evidence that civilization had crossed into a new technological condition. Human beings were beginning to depend on electrical pathways, whose behavior could be altered by forces originating far beyond any city, nation, or horizon. By the 1850s, the telegraph had begun to change the meaning of distance. For thousands of years, a message could travel no faster than the person, animal, ship, or vehicle carrying it. Even the most organized empires had lived within that limit. A ruler could issue an order, but the order still had to cross roads, rivers, mountains, or seas before another person could act on it. Telegraphy altered this ancient pattern by turning information into electrical signals that moved through wires. The physical world did not become smaller, but the time required for communication suddenly did. That change mattered most in places where timing already carried practical consequences. Railways, for example, were expanding across parts of Europe and North America, and trains moving along shared tracks required increasingly careful coordination. Telegraph lines could help stations exchange information about departures, arrivals, delays, and traffic. Merchants could learn about prices or shipments more quickly than before. Newspapers could receive reports from distant cities without waiting for a courier to complete the entire journey. Government offices could send instructions across long distances with a speed that would have seemed impossible only a generation earlier. None of these systems became perfectly reliable, and the spread of telegraph networks was uneven, but the principle was unmistakable. Human society had discovered how to separate the movement of information from the movement of people. This was a technological change, but it also touched something much older in human history. Our species had always survived by sharing information. Knowledge about water, weather, animals, routes, danger, food, and social relationships could determine what a group was able to do. For most of that history, communication depended on proximity and memory. Writing extended memory beyond a single mind. Roads and ships extended the reach of messages. The telegraph extended speed. It allowed distant decisions to become connected in near real time by the standards of the 19th century. Yet every new connection required physical infrastructure. Poles had to be raised. Wires had to be stretched across the landscape. Instruments had to be powered and maintained. Operators had to know how to send and interpret coded signals. The network therefore created a new layer of dependence beneath ordinary social life. If a horse became lame, one journey might slow. If a telegraph line failed, many messages using that route could stop at once. The scale of the vulnerability was still modest compared with the electrical systems that would appear later, but the pattern had begun. A network made communication faster because many places shared the same technical structure. The same shared structure meant that a disturbance affecting the network could be felt far beyond a single room or machine. This is where the story begins to move closer to 1859. Telegraph operators were learning to manage failures they understood, such as broken wires, damaged equipment, poor contacts, and local weather. But the wires also existed inside Earth's changing magnetic environment, whether anyone standing beside a telegraph key thought about that fact or not. Long conductors could respond to electrical effects produced during strong geomagnetic disturbances. The technology that conquered distance had therefore created an unexpected bridge between human communication and processes occurring far above the familiar world of roads and stations. For earlier generations, the sun could shine, darken behind clouds, or display unusual marks without touching a communication network, because no such network existed. By the middle of the 19th century, that was no longer true. The telegraph had given civilization a faster voice, and in doing so, it had quietly given the planet a new way to interfere with that voice. The achievement was useful, ordinary, and increasingly trusted. Each successful message encouraged more wires, more stations, and more dependence on rapid communication. Humanity was not preparing for a solar storm. It was simply building a better system, unaware that connection itself could become a pathway for disruption. By the late 1850s, telegraph lines no longer existed as isolated experiments connecting only a few nearby points. In many parts of Europe and North America, they had become expanding networks, following roads, railways, and commercial routes from one settlement to another. Wooden poles supported long stretches of metal wire across fields, forests, towns, and open country. At stations and offices, operators worked with batteries, keys, relays, and sounders, turning human language into coded electrical pulses and then back into words. The system was still young, but it already possessed one important quality of modern infrastructure. Many different people and institutions depended on the same physical network. A railway company might use a line to coordinate traffic. A newspaper might depend on it for reports from another city. A merchant might wait for information about prices, shipments, or orders. Government offices could exchange messages more quickly than traditional couriers allowed. The wires therefore carried more than electricity. They carried expectations about speed, timing, and connection. This was a new condition in human history. Earlier communication systems could link large territories, but their failures usually remained tied to physical movement. A blocked road slowed travelers. A damaged bridge interrupted a route. A storm at sea delayed a ship. Telegraphy introduced a different possibility. If an electrical disturbance affected a long conductor, the problem could appear in places separated by great distances yet joined by the same technology. The network did not need to be global in the modern sense for this to matter. It only needed enough length, enough conductivity, and enough dependence to make electrical behavior part of everyday communication. Human beings had spent most of their evolutionary history exchanging information through voices, gestures, memory, and face-to-face relationships. Even after writing emerged, information remained attached to clay, papyrus, parchment, paper, or other physical carriers. Telegraph wires changed that ancient arrangement by allowing information to move as electrical variation through metal. In doing so, they also placed communication inside a physical environment that extended far beyond the telegraph office. Every wire stood on Earth, and Earth itself possessed a magnetic field. That field was not perfectly static. It could change during disturbances associated with activity from the Sunday. 19th century scientists were still developing their understanding of electricity, magnetism, auroras, and solar phenomena, so the full chain connecting these things was not yet understood in the way it is today. Operators knew that their equipment could behave strangely. Scientists had already observed relationships between geomagnetic variation and auroral activity, but the practical meaning of a large solar disturbance for a growing telegraph network had not yet been demonstrated on the scale that would soon become famous. The network was therefore both an achievement and an unintended instrument. It was built to carry human messages, yet its long conductors could also respond to electrical currents induced during strong changes in the geomagnetic environment. No one needed to design the wires for that purpose. The laws of electromagnetism did not depend on human intention. This is one reason the year 1859 matters. Humanity had reached a moment when technology had become widespread enough to register a disturbance that earlier generations might have experienced mainly as unusual light in the sky. The same solar event occurring in a world without long electrical conductors would have left a different technological record. By placing metal lines across the landscape, people had unknowingly created sensitive pathways through which changes in the space environment could enter their machines. The telegraph network was still small compared with the power grids, communication systems, and satellite services of the future, but the basic relationship had appeared. Civilization had begun to connect itself electrically across distance, and once that connection existed, the behavior of the planet and the activity of the sun could become part of the history of human infrastructure. This was not yet the electrical civilization of the 20th or 21st century, but it was the beginning of a new exposure. A network built for human communication had become physically capable of responding to events originating far beyond the weather people could see. By 1859, the telegraph had become useful enough that people were beginning to trust it, yet the physical environment surrounding the wires was still only partly understood. Operators knew that circuits could behave strangely, batteries could weaken, contacts could fail, moisture could interfere with insulation. Lines could break in storms or be damaged by ordinary accidents. These were familiar problems because they belonged to the visible world of equipment and weather. What was far less obvious was that a telegraph line could also respond to changes in Earth's magnetic environment produced during powerful disturbances linked to the Sunday. The wires stretched across the ground as practical tools, but they were also long conductors embedded inside a planet with a magnetic field. That fact did not depend on whether anyone designing the network understood it. Science in the 19th century was making rapid progress in electricity and magnetism, and researchers had already established important connections between electrical currents and magnetic effects. Auroras and variations in Earth's magnetic field were also subjects of observation. Yet the modern framework of space weather did not exist. There were no spacecraft watching the sun, no satellites measuring the solar wind, no global warning centers, and no models capable of tracking a large eruption through interplanetary space toward Earth. The people using telegraph systems therefore lived inside a technological transition whose risks were still being discovered. This situation has a deep connection to the longer history of our species. Human beings have often adopted useful tools before understanding every environment in which those tools must operate. Fire was used long before chemistry explained combustion. Sailors crossed seas long before meteorology could describe storms with modern precision. Farmers worked with seasons long before climate science existed. Telegraphy followed the same broad pattern. Its usefulness came first. A fuller understanding of its vulnerabilities came later. The difference was that electrical communication connected distant places through a force that could be altered by conditions extending far beyond local weather. A disturbance beginning at the sun could interact with Earth's magnetic environment and, under the right conditions, produce electrical effects in long conductors on the ground. For a society accustomed to thinking about broken poles, damaged wires, and failing batteries, this was a very different category of problem. Nothing needed to strike the wire physically. No tree had to fall across it. No flood had to wash away a station. The surrounding electromagnetic environment itself could change. That possibility was difficult to recognize because it crossed boundaries that daily experience kept separate. The sun appeared in the sky. Magnetism belonged to compasses and laboratory instruments. Telegraph wires belonged to communication. The connection among them was real, but it was not yet part of ordinary technological thinking. This is why the growing telegraph network of 1,859 matters so much. It stood at the meeting point between an ancient natural process and a very new human invention. The sun had been active for billions of years. Earth had possessed its magnetic field throughout human history. What was new was a civilization rapidly laying long conductive networks across the landscape and beginning to depend on them. Humanity had created a pathway through which a large geomagnetic disturbance could become a technological event. The vulnerability was not a flaw hidden in one machine. It emerged from the relationship between the machine, the network, the planet, and the Sunday. For most earlier generations, an unusual aurora could be witnessed, remembered, recorded, or interpreted without disabling a communication technology, because no electrical communication network existed. In 1859, the same class of planetary disturbance could leave two records at once, one written across the night sky and another appearing inside instruments built to carry human messages. By the end of the 1850s, all of those pieces were finally present at the same time, waiting for an event strong enough to reveal how closely they had become connected. For centuries, people had looked at the sun mainly as a source of light, warmth, seasons, and time. But by the 19th century, astronomers were learning to treat its visible surface as something that could be observed systematically. One of the most important features they followed was the appearance of sunspots, darker regions that move across the face of the sun as it rotates. These spots had been recorded long before the 1850s, and telescopic observations had made them a regular subject of scientific study. Their presence revealed that the sun was not an unchanging disk. Its visible surface could alter from day to day, and groups of spots could appear, grow, change shape, and disappear. By the middle of the century, observers were also beginning to recognize patterns in how often sunspots appeared. The roughly 11-year sunspot cycle had been identified in the 1840s, giving astronomers a new way to think about solar activity as something that rose and fell over time rather than appearing at random. This was still far from the modern understanding of magnetic fields, plasma, solar flares, and coronal mass ejections. The sun of 19th century science was becoming more dynamic, but many of the physical mechanisms behind that activity remained unknown. Richard Carrington entered this world as a careful observer, rather than as someone searching for a catastrophe. Like other astronomers of his era, he used telescopic methods to study the positions and motions of sunspots across the solar disk. Such work required patience, repetition, and precise recording. A single observation meant little without comparison to many others. The value came from watching the same object over time and building a pattern from small changes. That method has deep roots in human behavior. Long before astronomy existed as a formal science, people watched the sky to recognize seasons, track time, and orient themselves across landscapes. What changed in the 19th century was the precision of the instruments and the questions being asked. The sky was no longer only a guide for travel or agriculture. It was becoming a physical system that could be measured. Carrington was especially interested in solar rotation and the movement of sunspots, and his observations contributed to a growing effort to map activity on the sun more carefully. This matters because the event associated with his name did not begin with telegraph wires sparking or auroras lighting distant skies. It began with someone looking closely at a region of the sun that already appeared unusually active. On the morning of the 1st of September, 1859, Carrington was observing a large group of sunspots. He was not watching the sun continuously with modern electronic instruments, and he had no satellite data, no solar images arriving from space, and no warning system describing what might happen near Earth. His tools belonged to a very different age, yet the basic act was familiar. Record what is visible, compare it with earlier observations, and avoid claiming more than the evidence allows. This is one reason his observation remains important. It sits at a boundary between older astronomy and modern space science. Human beings had spent thousands of years beneath the Sun, but only recently had they begun to examine its changing surface closely enough to connect unusual solar behavior with events that might later be measured on Earth. At the same time, researchers were comparing solar observations with changes measured in Earth's magnetic field and with reports of auroras. The relationships were suggestive, but the complete physical explanation was still beyond 19th century science. This uncertainty is important. The people watching sunspots were not secretly aware of a coming technological disaster. They were assembling separate pieces of evidence whose connections would become clearer only through later observations, experiments, and the development of modern solar physics. The wires below were expanding. The science above was becoming more precise. And on that September morning, both histories were about to meet. On the morning of the 1st of September 1859, Richard Carrington was observing the Sun from his private observatory in England, following a large and complex group of sunspots that had drawn the attention of solar observers. Because looking directly at the Sun through a telescope is dangerous, astronomers commonly projected the solar image onto a surface where details could be examined and drawn more safely. Carrington was using this kind of method when something unusual appeared within the sunspot region. Two intensely bright patches became visible against the projected image of the Sunday. They brightened rapidly, moved or changed in appearance over the following minutes, and then faded. The entire observation was brief. Carrington marked the positions of the bright features and later described what he had seen with the caution of an observer who understood that a single unexpected event could be difficult to interpret. Another English observer, Richard Hodgson, independently reported a similar phenomenon that day, strengthening the historical record that something genuinely unusual had occurred on the visible face of the Sunday. In modern terms, the event is generally identified as an exceptionally energetic white light solar flare, although 19th century astronomy did not yet possess the physical language needed to describe it in the way solar scientists do today. Carrington himself could not watch magnetic fields twist through hot plasma, measure radiation across wavelengths invisible to the eye, or detect material moving outward through space. He saw light. That distinction is important. The famous observation was not a complete view of a solar storm travelling toward Earth. It was one narrow human measurement made with the instruments available at the time. For most of human history, people had watched the Sun only from the ground, often without instruments, and unusual solar activity could pass unnoticed unless it produced a visible effect. By 1859, careful telescopic observation had created a new kind of memory. A fleeting change lasting only minutes could be sketched, timed, compared with other records, and preserved for later generations. Carrington therefore captured one small moment in a much larger physical process, without knowing how large that process might be. There was also an important scientific coincidence. Around the time of the bright solar observation, instruments monitoring Earth's magnetic field recorded a sudden disturbance. Carrington considered whether the two events might be related, but he did not present the connection as certain. That restraint matters because the causal chain linking solar eruptions, interplanetary space, and geomagnetic storms was not yet understood. Modern science can place his observation within a broader picture of solar activity, but it should not place modern knowledge inside Carrington's mind. He did not see a coronal mass ejection leaving the Sun, and no instrument in 1859 could follow such a structure across the space between the Sun and Earth. What he recorded was a visible signal from an active region, not a forecast. The deeper significance emerged only when events observed on Earth were considered alongside it. This is similar to the way human knowledge had developed across much of our history. First a pattern is noticed, then separate observations accumulate, and only later does a mechanism become clear. Early travellers could recognize seasonal stars without knowing stellar physics. Farmers could identify recurring weather patterns without understanding atmospheric circulation. Carrington could record a remarkable change on the Sun, while the full meaning of that change remained beyond the science of his century. The morning itself, therefore, did not announce what was coming. It left a careful mark in an observer's record, a brief brightness on the Sun followed by uncertainty. The answer would not appear in the telescope alone. It would emerge when the planet beneath that telescope began to respond. Within a short time, evidence would begin arriving from instruments and telegraph offices far from Carrington's observatory, showing that the quiet act of watching the sun had coincided with changes on Earth that no single observer could explain by looking upward. After the bright patches faded from Carrington's projected image, nothing visible remained that could tell him what was happening between the sun and Earth. Space appeared empty because the instruments of 1859 could not measure the stream of charged particles and magnetic structures that modern spacecraft now monitor. Today, scientists understand that major solar eruptions can send vast clouds of magnetized plasma outward from the sun, and when one of these eruptions is directed toward Earth, it can disturb the magnetic environment surrounding the planet. But applying that modern picture to an event observed more than a century and a half ago requires caution. No spacecraft measured the eruption associated with the Carrington Event, and no instrument followed its path through interplanetary space. Researchers reconstruct what probably happened from solar observations, magnetic records, auroral reports, and the behavior of telegraph systems. The evidence strongly supports the conclusion that Earth experienced an exceptionally intense geomagnetic disturbance associated with extreme solar activity, but many details of the journey from Sun to Earth cannot be recovered with the precision available for modern storms. This difference between what is known and what must be reconstructed is important. Human beings have always tried to understand distant causes from local traces. A footprint could reveal that an animal had passed without showing the entire journey. Smoke could indicate fire beyond the horizon without revealing its exact size. In the same way, 19th century observers could record changes in Earth's magnetic field, strange currents in telegraph wires, and brilliant auroras without seeing the solar material responsible for those effects moving across space. Modern science connects these traces through physics, but it should not turn uncertainty into a dramatic certainty simply because the story is easier to tell that way. What matters is the sequence. The sun was highly active. Carrington and Hodgson observed an extraordinary bright event in a sunspot region. Soon afterward, Earth's magnetic environment underwent a powerful disturbance, and the consequences appeared in places that had no direct physical connection to Carrington's telescope. Magnetic instruments responded. Auroras spread far beyond their usual high-latitude regions. Telegraph circuits began to behave in ways that operators could not explain through ordinary equipment failure alone. The importance of this sequence lies in scale. For most of human history, a disturbance originating on the sun could pass through space and interact with Earth without entering any technological network, because humanity had built none. By 1859, that condition had changed. The planet now carried long conducting wires designed to transmit small electrical signals between distant communities. When the geomagnetic environment changed strongly enough, those wires could become part of the response. A natural process that began far beyond the atmosphere could therefore produce effects inside machines on the ground. Nothing about this required the sun to attack Earth, and nothing about it implies that the entire 19th century world was close to destruction. The event became historically important because it revealed a relationship that technological civilization would later make much more consequential. Carrington's observation gave science a solar marker. Magnetic observatories provided another record. Telegraph operators provided a technological one. Auroral witnesses supplied a visible record across a wide geographical area. Seen separately, each piece was incomplete. Seen together, they formed an early outline of what is now called space weather, conditions originating from solar activity that can affect the near-Earth environment and human technology. The people of 1859 did not possess that modern concept, but they were living through one of the events that would eventually help make it necessary. This was the deeper historical transition. Earlier humans had lived beneath the same active star, but their communication systems were carried by voices, bodies, animals, paper, and roads. Now a disturbance in the space around Earth could leave a measurable signature inside infrastructure. The bright patches Carrington had watched were gone. The larger story, however, was moving away from the telescope and into the planet itself. When the geomagnetic disturbance reached Earth, the first technological effects did not appear as ruined cities or a civilization suddenly going dark. They appeared inside telegraph systems. Operators in different places reported circuits behaving in ways that did not match ordinary equipment failure. Signals became difficult to send or receive. Electrical currents appeared in wires even when the normal batteries were not providing them in the usual way. Instruments produced unexpected sparks, and communication became unreliable on affected lines. To understand why this mattered, it helps to remember how delicate telegraphy was. The system was designed to work with controlled electrical pulses moving through long conductors. Operators expected current to come from their batteries, travel along the wire, and activate equipment at another station. A strong geomagnetic disturbance could interfere with that arrangement by inducing additional electrical currents in long conducting paths. The wire itself had become a place where changes in Earth's magnetic environment could produce measurable electrical effects. Nothing had to strike the telegraph pole. No lightning bolt had to hit the office. The surrounding electromagnetic conditions had changed enough for the network to respond. For most of human history, there had been no comparable pathway into communication. A messenger carrying spoken or written information could be delayed by weather, terrain, injury, or distance. But a disturbance in Earth's magnetic field could not suddenly place an unwanted current inside the message. Telegraphy changed that relationship. Human beings had converted communication into controlled electricity, and natural changes in the planet's magnetic environment could now enter the same physical system. Reports from 1859 described telegraph operations being disrupted across broad areas, although the effects were not identical everywhere. Some circuits experienced severe interference, while others continued to function during portions of the disturbance. This unevenness is important because the Carrington event should not be described as though every telegraph line on Earth failed in exactly the same way. The effects depended on the design and orientation of lines, local conditions, electrical grounding, and the changing nature of the geomagnetic storm itself. Historical records are also incomplete, so modern accounts must avoid pretending that every detail can be reconstructed. What is clear is that the event demonstrated a physical connection between geomagnetic activity and electrical infrastructure on a scale difficult to ignore. The telegraph network, created to defeat distance, had unexpectedly become a detector of space weather. Operators who knew nothing about solar plasma could still observe the consequence because their instruments were responding to it. This was a new kind of evidence in human history. Earlier, people might have seen an aurora and recorded unusual light in the sky. The telegraph added another layer. A machine could register the disturbance even when the operator could not see its cause. The significance was not that 19th century society came close to ending. Most food production, water supply, transportation, manufacturing, and domestic life did not depend on electrical networks in the way they do today. The disruption was therefore limited by the technological structure of the age. Yet the principle exposed in those wires would become more important as civilization changed. Every later system built around long conductors, electrical power, precise timing, radio communication, or space-based technology would create new ways for solar activity to matter. In 1859, the warning was written not in a prediction but in behavior. Currents appeared where operators had not asked for them. Equipment responded to forces outside the telegraph office, and a network built by human hands revealed that the electrical environment of Earth could reach directly into technology. The event, therefore, marked a quiet boundary between two ages. Before electrical networks, solar disturbances could illuminate the sky without directly entering the machinery of communication. After telegraphy, the planet itself had become involved in the circuit in a practical sense. Humanity had not changed the sun, but it had built technology that could feel what the sun was doing. One of the most remarkable reports from the Carrington event eventually came from telegraph operators, who discovered that the unwanted current in their lines was not always merely an obstacle. In some cases, it became strong enough to help operate the equipment itself. Historical accounts describe telegraph circuits in North America continuing to transmit messages for a time after their normal batteries had been disconnected. The best-known examples involve operators on lines between Boston and Portland, where induced currents associated with a geomagnetic disturbance were reportedly sufficient to keep the circuit working intermittently. This did not mean that the sun was directly powering the telegraph in the ordinary sense, and it did not happen everywhere. The current was being produced through the interaction between a changing geomagnetic environment and long conducting paths on the ground. Under unusual conditions, That induced electricity entered the same wires normally controlled by telegraph batteries. For the operators, the effect must have appeared as a reversal of the usual logic of the machine. A telegraph system was designed so that people decided when current flowed. During the storm, current could appear without being requested, rise and fall unpredictably, and sometimes become useful enough to carry signals. The distinction between useful current and damaging current depended on strength, direction, timing, and the design of a particular circuit. Too little current could prevent a signal from being received. Too much could interfere with instruments, produce sparks, or make communication difficult. A naturally induced current could therefore help one line for a period while disrupting another. This uneven behavior is important because later retellings sometimes compress the event into a single dramatic image of telegraph machines operating by themselves. The historical reality was more complicated. Different lines experience different effects, and records survive unevenly. What can be said with confidence is that geomagnetically induced currents became strong enough on some telegraph systems to alter normal operation substantially, including documented periods when batteries were disconnected and communication continued. For a civilization only beginning to use electricity at scale, this was a remarkable demonstration of how a natural electromagnetic disturbance could enter human infrastructure. Throughout most of human history, energy used for communication came from muscles, animals, wind, or other visible sources. A messenger walked because muscles converted food into motion. A sailing vessel moved because air pressed against fabric. A telegraph message, by contrast, depended on carefully controlled electrical differences along metal conductors. Once communication entered that electrical world, Earth itself could become part of the circuit during a strong geomagnetic storm. The operators in 1859 did not need a modern theory of space weather to recognize that something unusual was happening. They could disconnect a battery and still observe electrical behavior in the line. The evidence was practical, immediate, and measurable through the machine in front of them. Yet the larger meaning was only beginning to emerge. The Carrington Event showed that technological systems could respond to environmental changes that originated far beyond ordinary weather. It also showed that the response was not simply a question of whether a machine survived or failed. Networks could behave in unexpected intermediate ways. Signals could become distorted. Current could appear where none was intended. And equipment could function under conditions for which it had never been designed. That lesson remains important when thinking about modern infrastructure. A complex electrical system does not always fail like a lamp being switched off. Disturbances can create abnormal currents, voltage problems, communication errors, protective responses, and cascading technical complications. The 19th century telegraph was far simpler than a modern power grid, but it revealed the basic relationship clearly. The network was connected across geography and also to geophysical conditions far beyond it. Human beings had built wires to command electricity, and for a brief time in 1859, the electrical environment of the planet showed that those wires could carry currents that no operator had chosen to create. The most important question about the technological damage of 1859 is not whether the telegraph behaved strangely, but how far that disturbance actually went. Historical reports describe interrupted communication, unexpected currents, sparks from telegraph equipment, and in some cases fires associated with the electrical systems. These accounts show that the geomagnetic storm was capable of producing effects strong enough to interfere with the technology of the time. They do not show that 19th century civilization was on the edge of collapse. Telegraphy was important, but it was still only one layer of a society whose essential functions remained largely mechanical, biological, and local. Food did not depend on electrically controlled refrigeration networks. Water systems were not managed by digital sensors. Banking records were not stored on remote servers. Navigation did not rely on satellites. A telegraph failure could delay information, disrupt railway communication, interrupt business, and create confusion. But most daily life continued through systems that did not require electricity. This difference is central to understanding what the Carrington Event really did. It exposed a new technological vulnerability without producing the kind of global systemic failure that modern imaginations sometimes project backward onto 1859. Even the dramatic reports from telegraph offices need to be read carefully. Sparks could jump from equipment when induced currents became unusually strong. Operators sometimes disconnected batteries because the lines were carrying unwanted electricity. Some reports describe paper or equipment being scorched or ignited. These observations are historically meaningful because they reveal the intensity of the electrical disturbance inside particular circuits. Yet they should not be expanded into claims of widespread urban fires or universal destruction. The surviving record is incomplete, and the conditions varied from one line to another. A long conductor running in one direction could respond differently from another line elsewhere. Grounding, equipment design, local geology, and the changing structure of the geomagnetic disturbance could all influence what operators experienced. The event therefore produced a patchwork of effects rather than a single identical failure across every connected region. This is also why the telegraph record is so valuable. Human beings had spent nearly all of their history using communication methods that could fail for familiar reasons. A messenger could be delayed, a road could become impassable, a ship could be lost. In 1859, communication failed for a reason that could not be seen by looking at the road outside the office. The wires remained standing, yet the electrical environment surrounding them had changed. Technology had become sensitive to a layer of nature that earlier generations rarely had any practical reason to consider. The lesson was not that electricity itself was unsafe. The lesson was that a network can inherit vulnerabilities from the physical environment through which it operates. That principle would become more important as later generations surrounded themselves with longer power lines, transformers, radio systems, satellites, and electronic devices. In the world of 1859, the consequences were contained partly because electrical dependence was still shallow. A disrupted telegraph network was serious, but it did not automatically stop food production, water distribution, household heating, transportation, finance, hospitals, and communication all at once. Modern society is structured differently, which is why the Carrington event matters today even though its original damage was limited by the age in which it occurred. Its historical value lies in the clarity of the demonstration. A natural disturbance originating far from Earth entered human technology through long conductors, created currents that operators did not control, disrupted communication, produced sparks, and in some documented cases contributed to small fires or equipment damage. Nothing more dramatic is needed to make the event important. The cold fact is simpler. The first electrical networks were already capable of being disturbed by the sun, and humanity had only just begun building them. It also revealed an asymmetry that would grow with technological progress. As civilization transferred more essential tasks into electrical systems, disturbances capable of entering those systems could matter more. The night sky of 1859 carried another record of the storm, one that could be seen without wires, batteries, or scientific instruments. Auroras appeared across regions far beyond the high latitudes where people were most accustomed to seeing them. Reports from the Great Auroral Storm describe displays reaching unusually low geomagnetic latitudes, with lights visible across broad parts of North America and elsewhere. Modern historical studies of the event have found observations extending to remarkably low latitudes, evidence that Earth's magnetic environment had been disturbed on an exceptional scale. The important point is not that every witness saw the same colours or shapes. Auroras vary in form, brightness, motion, and colour, and 19th century descriptions were written by people with different expectations, languages, and levels of scientific knowledge. What connects the reports is their geographical reach. A phenomenon usually associated with the far north or south became visible to populations who rarely encountered it. For many people, the sky itself had become unfamiliar, yet this light was not the storm striking the ground. Aurora is produced high in the atmosphere when energetic particles and magnetic processes associated with space weather led atoms and molecules to emit light. During strong geomagnetic storms, the regions in which auroras occur can expand toward lower latitudes. The 1859 displays therefore offered a visible sign that the disturbance extended through the near-Earth environment on a very large scale. This matters because the telegraph problems could otherwise be imagined as a collection of unrelated technical failures. A faulty battery in one office could explain one problem, a damaged wire could explain another. But when Unusual electrical behavior appeared across distant telegraph systems while extraordinary auroras spread across the sky. The events began to point towards something larger than local equipment trouble. Human beings had watched auroras for thousands of years, long before anyone understood their physical cause. They entered oral traditions, chronicles, diaries, scientific records, and personal memory. For our distant ancestors, such displays could be striking, but they did not interfere with electrical networks because no such networks existed. By 1859, the same natural phenomenon appeared over a civilization that had started to build long conducting paths across the ground. The sky and the wires were now producing two different kinds of evidence from the same disturbed planetary environment. One could be seen by anyone looking upward. The other appeared inside machines built to carry messages. This combination is what makes the event so useful scientifically and historically. The auroras showed that the disturbance was not confined to one telegraph route, one city, or one country. The affected magnetic environment surrounded the planet, although the intensity and visible consequences varied by location. It is also important not to turn eyewitness reports into measurements they were never meant to be. A person describing a red glow near the horizon was not recording modern satellite data. Historical observations help researchers estimate the extent of the storm, but they contain uncertainty. Even so, the overall pattern is clear enough. The auroral zone expanded far beyond its ordinary range during the Great Storm. The result was a rare moment when a process beginning at the sun became visible across huge areas of the human world. The people below could not see magnetic fields or charged particles traveling through space. They could only see the sky changing above them and, in telegraph offices, watch currents appear in wires below. Together, those two records revealed that the disturbance belonged neither to the sun alone nor to the telegraph alone. It involved the space between them, Earth's magnetic environment, and a technological civilization that had only recently become capable of noticing the connection. For the first time, a solar disturbance was being recorded simultaneously by human eyes, magnetic instruments, and an expanding electrical network. The ancient sky had not changed its nature, but humanity now possessed new systems that could register its effects in several ways. Across the night surrounding the great geomagnetic disturbance of 1859, people in widely separated places looked upward and described a sky that did not resemble an ordinary night. Some reports spoke of red glows, others of shifting curtains or bands of light, and many emphasized that the illumination appeared much farther from the polar regions than auroras were usually expected. These accounts survive in newspapers, scientific records, diaries, and other historical documents, but they have to be handled carefully. A witness describing color or brightness was not using a modern instrument, and two people standing in different places could see different portions of the same large display. Their words, therefore, cannot be treated as exact measurements. What matters is the pattern created when many independent observations are considered together. The auroral activity covered an unusually broad geographical range, and that broad range matched the evidence that Earth's magnetic environment was undergoing an intense disturbance. For people alive at the time, however, there was no single global screen on which all of these observations appeared at once. A person in one town could see only the sky above that location. A telegraph operator could know only what was happening on the line connected to the office. An astronomer could record changes in an instrument without immediately knowing what observers elsewhere were experiencing. The larger event became visible only when information from different places was collected and compared. In this sense, the Carrington Event sits at an interesting moment in human history. Our species had always learned about large natural events by combining local experience. Hunters could follow animal movement from tracks left in separate places. Coastal communities could compare tides, winds, and storms across generations. Farmers could remember how seasons differed from one year to another. By 1859, printing, scientific correspondence, newspapers, and telegraphy allowed observations from distant regions to be gathered more quickly than earlier societies could have managed. The same communication technology that was being disturbed by the storm also helped people learn that the disturbance extended beyond their own horizon. Yet the reports should not be transformed into a dramatic story in which everyone believed the world was ending. Historical witnesses interpreted unusual auroras through the knowledge and culture available to them. and reactions varied. Some people were familiar with auroral displays, while others lived in regions where such lights were rare. The scientifically useful point is simpler. The sky offered a visible record across a large area, and the geographical spread of those observations became evidence about the scale of the geomagnetic storm. This record also reminds us that the Carrington event was not defined by a single spectacular moment. It was a collection of connected observations made from different positions on Earth. A bright solar event seen through telescopes, disturbances recorded by magnetic instruments, abnormal currents detected in telegraph wires, and auroras observed across unusually low latitudes. No single witness possessed the entire picture. The event existed on a scale larger than ordinary human perception. Only by joining records across space could later researchers see how the pieces related. That method remains central to modern space weather science, although the instruments are now very different. Satellites watch the sun, sensors measure the near-Earth environment, magnetometers track changes in the magnetic field, and technological systems provide additional evidence of disturbance. The principle, however, is familiar. A planetary event is understood by combining many local measurements into one physical picture. In 1859, that picture was still incomplete, but the evidence scattered across the world was already pointing toward it. People beneath different skies were witnessing different expressions of the same disturbed environment, and together their records showed that the event could not be confined to one observatory, one telegraph office, or one nation. The human scale of the experience was local, but the physical scale was planetary. That difference is one of the quiet lessons preserved in the old reports. Natural systems do not respect the boundaries by which people divide maps, and understanding them often requires observations made by many people who never meet one another. Seen from the ground, the events of 1859 appeared separate. An astronomer in England watched a brief brightening on the Sunday. A telegraph operator elsewhere struggled with currents that did not behave as expected. People far from the polar regions looked upward and saw auroral light in unfamiliar parts of the sky. Magnetic observatories recorded sharp changes in instruments designed to measure Earth's field. No single observer could stand in one place and see the physical system connecting all of these experiences. Modern science provides that larger view. Earth is surrounded by a magnetic environment shaped by the planet's own field and continuously influenced by the solar wind, the stream of charged particles and magnetic field carried outward from the Sunday. When strongly disturbed solar material and its magnetic field interact with this environment under favorable conditions, energy can be transferred into the magnetosphere and upper atmosphere. The result can include an intense geomagnetic storm, expanded auroral activity, and electrical effects that reach conducting systems on the ground. In 1859, people did not yet possess this complete framework, but their scattered observations preserved evidence from several different layers of the same event. The aurora was therefore more than an unusual light display. It was a visible expression of changes occurring in the near-Earth environment, while the telegraph disturbances were technological expressions of related geomagnetic changes closer to the ground. This does not mean that every auroral feature can be matched directly to a particular spark in a telegraph office. The physical system is more complicated than that, and historical measurements are incomplete. The safer conclusion is broader. Both kinds of observations belong to an exceptionally disturbed period in Earth's magnetic environment associated with intense solar activity. That perspective changes the scale of the story. Human beings evolved on the surface of a planet that has always existed inside a larger space environment, even though our senses give us little direct awareness of it. We feel wind and rain against the skin. We see clouds cross the sky. We do not feel the solar wind flowing past Earth, and we cannot see the magnetosphere with our eyes. For most of human history, that invisibility hardly mattered to technology, because there was little technology capable of responding to such changes. The aurora could appear, vanish, and become part of memory without entering a network of essential machines. The telegraph changed that relationship. Now the same planetary disturbance that produced light high in the atmosphere could also alter electrical currents in long wires below. The sky and the network were not separate stories. They were two ways in which a single disturbed environment became observable to a species that had recently begun surrounding itself with electrical conductors. This is why the geographical spread of the 1,859 auroras matters so much. It helps show that the event could not be reduced to a malfunction in one country or a strange observation at one telescope. Earth as a whole was participating in a changing electromagnetic system, even though the effects differed from place to place. The planet was not being physically struck like an object hit by a projectile. Instead, fields, particles, currents, and the upper atmosphere were interacting across enormous distances. That distinction is quieter than the language of catastrophe, but it is more revealing. The Carrington Event demonstrated that the boundary between human technology and space was already becoming thin. A wire resting on the ground could respond to conditions whose origin lay far beyond the atmosphere. A light appearing over one community could be related to magnetic measurements made thousands of kilometers away. Once these observations were placed together, the event became larger than any individual witness. It became evidence that civilization exists not only on Earth's surface, but inside a dynamic environment extending from the ground into space, an environment that modern society would eventually depend on understanding. The people of 1,859 had only begun to recognize that connection, but the planet had already demonstrated that the sky above human civilization and the technology beneath it could belong to the same physical system. The sun can look calm from Earth because its surface is too distant for our eyes to resolve without instruments, but physically it is an active star shaped by heat, motion, and magnetic fields. Unlike a solid object, the visible surface of the sun is made of hot plasma, a state of matter in which charged particles move freely. Because the sun rotates and its internal material moves, its magnetic field becomes complex over time. In some regions, magnetic field lines can become concentrated, twisted, and stressed. Sunspots are visible signs of this activity, appearing darker than their surroundings because they are cooler than nearby regions, although they remain extremely hot by ordinary standards. The important point is that sunspots themselves are not the storm. They are regions associated with strong magnetic fields, and active regions around them can produce several different kinds of solar events. One of these is a solar flare. A flare is a rapid release of energy in the sun's atmosphere, producing intense radiation across a broad range of wavelengths. This can affect parts of Earth's upper atmosphere and interfere with some forms of radio communication when conditions are strong enough. But a flare is not the same thing as a large cloud of matter traveling through space. Another phenomenon, called a coronal mass ejection, or CME, involves a large eruption of magnetized plasma from the sun's outer atmosphere. A CME can carry charged particles and an embedded magnetic field outward through the solar system. Some CMEs travel in directions that never bring them near Earth. Others are directed partly or strongly toward our planet. Even then, the effect at Earth depends on more than size alone. The orientation of the magnetic field carried by the arriving material can strongly influence how efficiently energy enters Earth's magnetic environment. This is why two solar eruptions that appear impressive near the Sun do not necessarily produce the same consequences on Earth. Solar flares and CMEs can occur together, but they are physically distinct phenomena. A flare is primarily an intense release of electromagnetic radiation, while a CME is an eruption of magnetized plasma moving outward through space. Keeping those ideas separate makes the Carrington Event easier to understand. Carrington and Hodgson observed a brilliant white light flare in 1859, but they could not observe the associated material leaving the sun in the way modern spacecraft can. The later geomagnetic storm indicates that Earth encountered an exceptionally disturbed solar-driven environment, but the exact properties of the eruption have to be reconstructed from historical evidence. Our ancestors experienced sunlight, seasons, heat, and darkness directly, while the magnetic processes occurring on the sun remained beyond perception. Once electrical networks appeared, invisible solar processes gained practical importance. A flare could alter the ionized upper atmosphere. A CME, when directed toward Earth and magnetically favorable for strong coupling, could disturb the magnetosphere and contribute to a geomagnetic storm. Those effects could then reach technologies built within and around Earth. The chain therefore contains several stages, and each stage matters. Solar activity does not automatically become a geomagnetic storm, and a geomagnetic storm does not automatically destroy technology. The outcome depends on the nature of the solar eruption, its direction, its magnetic structure, Earth's near-space environment, and the design of systems exposed to the disturbance. This explanation is less dramatic than imagining the Sun firing a single destructive blast at Earth, but it is closer to the physics. The Carrington Event matters because it shows how ordinary physical processes, when unusually intense and aligned in the right way, can connect an active region on the Sun to wires resting on the ground. Human civilization did not create the solar activity. It created technologies that made that activity newly consequential. For most earlier generations, this activity remained part of a natural background that could be seen in sunlight or aurora without directly entering a technological network. Earth is not exposed to the solar wind in the same way that an unprotected rock would. The planet generates a magnetic field that extends far beyond the atmosphere and forms a vast region called the magnetosphere. This region is shaped by the continuous flow of solar plasma and magnetic field carried outward from the sunday. On the side facing the sun, the solar wind presses against Earth's magnetic environment and compresses it. On the opposite side, the field is stretched into a long magnetic tail. The shape is never perfectly fixed because the solar wind itself changes. Its speed, density, and magnetic orientation vary, and large solar eruptions can disturb it far more strongly than ordinary conditions do. The magnetosphere therefore acts less like a rigid wall and more like a dynamic system that responds to what arrives from the sunday. Most of the time, this response is manageable and produces no serious effect on technology. During stronger disturbances, however, energy can enter the magnetosphere more efficiently. One important factor is the direction of the magnetic field carried by the solar wind, or an arriving coronal mass ejection. When that field is oriented in a way that favors magnetic reconnection with Earth's field, energy can be transferred into the near-Earth environment. The exact process involves plasma and magnetic fields interacting across enormous distances, but the basic idea is simple. The Sun does not need to send matter directly into cities or machines. It can disturb the magnetic system surrounding the planet, and that disturbance can then alter currents in space and in the upper atmosphere. These changes can expand the regions where auroras appear and can produce rapid variations in the magnetic field measured at Earth's surface. Human beings evolved entirely inside this magnetic environment without being able to see it. Our bodies do not sense the magnetosphere in the way our skin senses wind or temperature. For most of human history, that invisibility had little technological importance. A family carrying food, a community following a river, or a ship guided by stars did not depend on long electrical conductors or orbiting electronics. The magnetic environment could change without directly entering most tools people used. Once electrical networks appeared, the situation became different. A strong geomagnetic storm could create changing magnetic conditions around Earth, and those changes could influence long conductive systems on the ground. This is the bridge between the sky of 1859 and the telegraph office. Carrington's observation was made at the Sun, but the telegraph effects occurred because Earth's own magnetic environment responded to intense solar activity. The planet was not passive. Its field interacted with the incoming disturbance and redistributed energy through a complex system of currents and magnetic changes. Auroras were one visible result. Geomagnetically induced currents in long conductors were another. Modern measurements have made this chain much clearer than it was in the 19th century. Spacecraft can sample the solar wind before it reaches Earth. Satellites can monitor the magnetosphere, and ground instruments can track magnetic variation. Yet the basic physical relationship remains the same as it was in 1859. Earth's magnetic field protects the surface from much of the direct influence of charged solar material. But protection does not mean complete isolation. Under strong conditions, the magnetosphere can become highly disturbed. The consequence depends not only on how active the Sun is, but on how the arriving magnetic field interacts with Earth and on what human systems are present to respond. The same geomagnetic disturbance that might once have produced little more than an extraordinary aurora can matter differently in a civilization covered by electrical networks. This distinction prevents a common misunderstanding. A geomagnetic storm is not simply radiation passing through the magnetic field and striking electrical equipment. It is a response of the coupled Sun-Earth system, with changing currents and fields creating conditions that technology can detect. The natural process is ancient. The vulnerability is largely technological. A geomagnetic storm becomes technologically important on the ground when changing magnetic conditions create electric fields that drive currents through long conducting paths. The idea follows a basic principle of electromagnetism. When the magnetic environment changes with time, electrical effects can be induced in nearby conductors. During a strong geomagnetic disturbance, large electrical current systems in the magnetosphere and upper atmosphere change, and the magnetic field measured at Earth's surface can change with them. Those variations can produce electric fields in the ground. If a long conductor lies across that environment, current can begin to flow through it, even though no generator or battery was intentionally supplying that current. This is what made the telegraph wires of 1859 so revealing. They were long pieces of metal extending across the landscape, connected through equipment and grounding arrangements that allowed naturally induced electrical currents to enter the circuits. The wires had been built to carry controlled signals, yet the changing geomagnetic environment created additional currents that operators had never requested. Some of those currents interfered with communication, some produced sparks, and on certain lines they became strong enough for operators to work temporarily without the normal batteries. The underlying process is often called geomagnetic induction. It does not require solar particles to travel down through the atmosphere and strike a wire directly. Instead, solar activity disturbs Earth's magnetic environment. That disturbance produces changing magnetic fields at the surface, and those changes can generate electric fields that drive currents through conducting systems. The length and orientation of a conductor matter, as do the electrical properties of the ground beneath it and the way the system is designed and grounded. This is one reason a geomagnetic storm does not produce identical effects everywhere. Two networks exposed to the same large storm can experience different levels of induced current because their physical environments and engineering are different. The geology below the surface can also influence how electric fields develop, adding another layer of regional variation. This connection between sky, ground, and technology would have been almost meaningless to most of our ancestors. For the overwhelming majority of human history, there were no long metal networks crossing continents. People carried information in memory, speech, writing, and physical objects. Natural geomagnetic induction could occur, but there was little human infrastructure through which the resulting currents could become socially important. Telegraphy changed that. Later, high-voltage transmission lines and other large conducting networks extended the same basic vulnerability into a civilization far more dependent on electricity. A modern power grid is not simply a larger telegraph, and its behavior during geomagnetic storms involves different equipment and engineering concerns. Yet the physical bridge is related. Changing geomagnetic fields can produce slowly varying currents in long conductors. In power systems, these geomagnetically induced currents can enter transformers and transmission networks, creating operating difficulties under sufficiently strong conditions. This does not mean that every solar storm damages a grid or that every transformer exposed to a geomagnetic storm will fail. The outcome depends on storm intensity, location, network configuration, equipment design, protective actions, and many other factors. The Carrington event therefore becomes scientifically useful not because it proves what a future storm must do, but because it demonstrates the pathway. Activity on the Sun can disturb the magnetic environment around Earth. Rapid magnetic changes can create electric fields at the surface. Long human conductors can carry currents produced by those fields. Once civilization began building large electrical networks, the distance between solar activity and human technology effectively became shorter. Nothing physical had changed about the distance from Earth to the Sunday. What changed was the existence of infrastructure capable of converting a planetary magnetic disturbance into an electrical problem inside machines. That is the quiet mechanism behind the sparks of 1859, and it is the reason the same historical event remains relevant to the electrical world built long after Carrington watched the Sunday. The world that experienced the Carrington event in 1859 was connected by electricity, but only lightly. Telegraph wires carried messages across growing distances, yet most of the physical work of civilization still continued without electrical power. Horses moved goods through streets. Steam engines pulled trains and powered machinery. Ships crossed oceans without satellite navigation. Food could be produced, stored, transported, and sold without a national electrical grid. Water systems, homes, factories, hospitals, and government offices were not tied together through digital networks. If telegraph communication failed for several hours, the disruption could be serious, but much of society could continue functioning through older systems that had existed before electricity. The modern world is built on a very different foundation. Electrical transmission lines now stretch across enormous regions, carrying power between generating stations, substations, cities, industries, and homes. Transformers change voltage so electricity can move efficiently over long distances and then be delivered where it is needed. Control centers balance supply and demand across networks that operate continuously. A power grid is therefore not simply a collection of wires. It is a coordinated system in which many components must work together, often across large geographical areas. This creates capabilities that would have been unimaginable to people living in Carrington's century. Electricity supports lighting, refrigeration, manufacturing, water pumping, telecommunications, data centers, transportation systems, medical equipment, financial services, and countless ordinary devices. Yet the same expansion changes what a severe geomagnetic storm could mean. Telegraph wires in 1859 demonstrated that long conductors can carry currents produced by geomagnetic disturbances. Modern high-voltage transmission systems also contain long conductors connected through transformers and grounding points. During sufficiently strong geomagnetic activity, slowly varying geomagnetically induced currents can enter parts of these networks. These currents are different from the alternating current that power systems are designed primarily to handle. Under some conditions, they can interfere with transformer operation, increase reactive power demands, contribute to voltage instability, or trigger protective responses. None of this means that a strong solar storm automatically destroys a national grid. Power systems vary greatly in design, geography, equipment, operating procedures, and preparation. The effect of a geomagnetic storm also depends on where the strongest magnetic changes occur and how quickly they vary. A network at one latitude may experience conditions different from another network. The geology beneath the ground can influence induced electric fields. The orientation and length of transmission lines matter. Operators can also take protective actions when warnings are available. The modern risk is therefore not a simple equation in which a Carrington-sized event produces one predetermined outcome. What has changed since 1859 is the number of systems that depend on electricity functioning reliably. For most of human evolution, energy for survival was distributed across bodies: fire, food, wood, animals, water, and local environments. Even early industrial societies used many independent forms of energy. Modern civilization has concentrated an extraordinary range of activities onto electrical infrastructure. A supermarket depends on refrigeration and electronic logistics. Urban water systems often depend on electrically powered pumps and treatment equipment. Mobile communication depends on powered base stations and data networks. Hospitals rely on electricity even when backup systems are available. Fuel distribution, financial transactions, transportation signaling, and information services all contain electrical dependencies. This does not make modern society weaker in every sense. Modern engineering also gives us redundancy, emergency generation, forecasting, repair systems, international cooperation, and scientific knowledge unavailable in 1859. The difference is that an electrical disturbance can now intersect with far more functions at once. The telegraph operators of Carrington's time discovered that the sun could place unwanted current inside a communication wire. Their experience was limited by how little of society was electrified. We inherited the same physical planet and the same active sun, but we built a much larger electrical architecture between them. The question raised by 1859 is therefore not whether modern civilization would experience an exact repetition of 19th century telegraph failures. It is how the same underlying physics would interact with a world in which electricity has become a basic condition for normal life. The wires have grown longer, the networks more interconnected, and the number of people depending on them far greater. What changed most after Carrington was not the Sunday, It was the scale of what humanity placed inside the electrical system. A modern power grid is designed to move enormous amounts of electrical energy over long distances while keeping voltage and frequency within carefully controlled limits. Under normal conditions, the alternating current flowing through transmission lines changes direction many times each second, and transformers are built to operate within that expected pattern. A geomagnetic storm introduces a different kind of electrical influence. When Earth's magnetic field changes strongly enough, electric fields can develop at the surface and drive slowly varying currents through long conductors. In a power network, those geomagnetically induced currents can enter transmission lines through grounded connections and pass through transformer windings. They do not behave like the ordinary alternating current for which the equipment was designed. This difference matters because the magnetic core of a transformer can be pushed away from its normal operating condition. Engineers describe one possible result as partial saturation of the transformer core. When that happens, the transformer can draw additional reactive power, produce unusual harmonics, experience increased heating in some components, and make voltage control more difficult. None of these effects automatically means that a transformer will be destroyed. A power system can experience abnormal conditions without suffering permanent damage, and protective equipment may disconnect components before more serious problems develop. The risk depends on many details, including the strength and rate of change of the geomagnetic disturbance, the length and direction of transmission lines, the electrical configuration of the network, the design of transformers, and the conductivity of the ground beneath the system. This is why a simple statement that a solar storm will burn out every transformer is scientifically misleading. The real problem is more conditional and more interesting. A storm can place stresses into a network that was designed for a different electrical environment, and those stresses may interact with the way the grid is operating at that moment. A heavily loaded system may respond differently from one with more available margin. One region may experience larger induced electric fields than another. A line running in one direction may collect a different voltage from a line with another orientation. Local geology can also change the electric fields produced at the surface. The same solar disturbance can therefore create an uneven geographical pattern of risk. This is another place where the history of human technology matters. Our ancestors lived within Earth's magnetic environment for countless generations without building continent-scale conductive networks. The natural process existed, but there was little infrastructure through which it could become a widespread engineering concern. The telegraph provided the first clear technological demonstration. The modern grid magnifies the importance of the same basic physical relationship because its conductors are longer, its equipment carries far greater power, and society depends on the service it provides. Yet modern engineering also changes the story in the opposite direction. Grid operators can monitor space weather alerts, adjust operating conditions, postpone maintenance, increase awareness of vulnerable equipment, and take other protective measures when a significant disturbance is expected. Networks also contain relays, breakers, monitoring systems, and operating procedures that did not exist in 1859. The modern world is therefore both more exposed and more capable of responding. That balance is essential when asking what a Carrington-scale event might mean today. The physical mechanism is real, but the outcome is not predetermined. A severe geomagnetic storm could create substantial operational challenges in some power systems, and historical storms have already demonstrated that geomagnetic activity can contribute to serious grid disturbances. But the effects would depend on where the strongest geoelectric fields developed and how individual networks reacted. What makes the Carrington event relevant is not a guarantee of global failure. It is the reminder that electrical infrastructure is physically connected to the environment in which it is built. The grid may appear to belong entirely to cities, substations, control rooms, and human engineering, yet its long conductors rest on a planet whose magnetic field can change. In 1859, that fact appeared as unwanted current in telegraph wires. In the modern age, the same principle reaches into systems carrying far more energy and supporting far more of daily life. The vulnerability does not come from electricity alone. It comes from scale, connection, and dependence. The greatest difference between 1859 and the modern world is not simply that today's machines are more delicate. It is that many essential systems now depend on one another, and electricity sits underneath a large share of them. A power interruption, therefore, does not remain only an electrical problem. It can become a water problem if pumps lose power, a communication problem if network equipment and mobile towers lose service, a transportation problem if signaling and control systems are affected, and a medical problem if hospitals must rely on backup generation. Modern societies have built layers of resilience against these failures, including batteries, generators, redundant connections, emergency procedures and repair teams. Yet those protections also depend on fuel, maintenance, communication, transportation, and people being able to reach the places where they are needed. This is why dependence matters as much as physical vulnerability. A transformer does not need to be permanently destroyed for a disruption to become important. If enough components must be taken offline, if voltage becomes difficult to manage, or if power is unavailable across a large enough area, other services can begin operating under stress. Water treatment plants may continue on backup systems for a time. Data centers may switch to generators. Hospitals may preserve critical loads. Telecommunications networks may use batteries. These measures are designed precisely because interruptions happen, but they are not identical everywhere and they are not unlimited. The question is how many systems are affected, for how long, and whether the supporting networks needed for recovery remain available. For most of human history, essential activities were distributed across many local forms of energy and labor. Food could be grown with human and animal power. Water could be carried or drawn locally. Messages moved independently of electrical grids. A failure in one tool did not automatically remove the energy source for several unrelated services. Modern civilization gained enormous efficiency by connecting these functions to shared infrastructure. A single electrical network can power thousands of pumps, factories, homes, hospitals, servers, and transport systems. That concentration is one of the reasons modern life is productive and coordinated. It also means that electricity can become a common dependency connecting problems that appear unrelated. This is the more useful way to think about a severe geomagnetic storm. The central concern is not that sunlight suddenly switches off every machine. Solar activity can disturb the geomagnetic environment, induced currents can place stress on parts of a power network, and power system problems can then interact with services that depend on electricity. Each step contains uncertainty, engineering safeguards, and regional differences. A serious disturbance in one region does not imply identical consequences everywhere else. Some grids may experience limited effects, while others could face greater operational challenges depending on location, geology, network design, and the storm itself. The same is true for recovery. Modern societies have repair crews, spare equipment, mutual assistance agreements, emergency planning, and the ability to reroute power or isolate damaged components. These capabilities make the present very different from a helpless civilization waiting for a solar event. At the same time, recovery becomes harder when several supporting systems are strained together. Fuel deliveries require transportation. Repair coordination requires communication. Water and sanitation need power. Digital systems often rely on both electricity and telecommunications. The vulnerability is therefore not best described as weakness. It is interdependence. The people of 1859 had far fewer electrical capabilities, but they also had far fewer essential functions tied to electrical networks. We have gained extraordinary power by connecting our systems, and the price of that connection is that disturbances can travel through society in ways our ancestors never experienced. The Carrington Event did not reveal that technology was a mistake. It revealed a physical fact that becomes more important with every layer of dependence we add. When many human systems share the same foundation, protecting that foundation becomes part of protecting everything built above it. Modern civilization extends far beyond the surface of Earth. Thousands of satellites move through near-Earth space, supporting communication, weather forecasting, navigation, scientific observation, and emergency services. Unlike a transformer sitting behind layers of atmosphere and ground infrastructure, a satellite operates directly inside the space environment that responds to solar activity. This does not mean that every satellite is constantly in danger. Spacecraft are designed with that environment in mind, and operators use shielding, redundant systems, software protections, and operational procedures to reduce risk. but intense solar activity can change the conditions around a satellite in several ways at once. Energetic particles can penetrate spacecraft materials and deposit charge inside electronic components. Charge can also build up on surfaces, creating electrical differences that may lead to discharges. In some circumstances, radiation can disturb electronics, corrupt stored information, or cause temporary faults in computer systems. Engineers often design spacecraft so that certain errors can be detected and corrected, and a temporary anomaly does not necessarily become permanent damage. The atmosphere itself can also change during strong solar and geomagnetic activity. Energy deposited in the upper atmosphere can heat and expand it, increasing atmospheric drag on satellites in low Earth orbit. The air there is extraordinarily thin, but small density changes can still alter satellite motion over time. Operators may need to update orbital predictions or perform maneuvers when conditions require it. A stronger disturbance does not therefore produce one universal satellite failure. It creates a different operating environment, and the consequences depend on altitude, spacecraft design, shielding, orientation, mission type, and the form of solar activity involved. This is another example of how technological vulnerability changes as civilization moves into new environments. Our earliest ancestors lived entirely on the ground beneath the atmosphere. Their tools experienced rain, cold, heat, wind, and the mechanical forces of the landscape. They had no machines orbiting through regions filled with charged particles and changing magnetic fields. Once humans placed infrastructure above most of the atmosphere, space weather became an engineering condition rather than only a distant natural process. The same sun that had illuminated human life for countless generations now interacted with machines operating where no earlier generation could reach. Satellite risk also differs from the geomagnetically induced currents that affect long conductors on the ground. A power grid is influenced mainly through electrical fields produced by changing geomagnetic conditions at Earth's surface. Satellites can be affected directly by radiation, energetic particles, charging, changes in the upper atmosphere, and disturbances in the space environment through which they travel. These processes can occur together during strong solar activity, but they should not be collapsed into a single idea of the sun simply frying electronics. Modern spacecraft are not all built the same way, and many continue operating through significant space weather events. Some systems can enter protective modes. Operators can postpone sensitive operations or reconfigure equipment when warnings are available. Satellite constellations can also provide redundancy if individual spacecraft experience problems. Yet even temporary degradation can matter. Weather observations, communications, navigation services, timing signals, and Earth observation may rely on spacecraft distributed across different orbits. A severe disturbance could therefore create operational challenges in several systems at once without requiring every satellite to fail. The realistic concern is not a cinematic sky suddenly emptied of functioning spacecraft. It is a period in which the environment above Earth becomes more difficult for machines to operate in, increasing the chance of anomalies, degraded performance, orbital uncertainty, and service interruptions. The Carrington Event occurred before humans had placed a single satellite in orbit, so it tells us nothing directly about how a modern satellite fleet would respond. What it does tell us is that the sun can drive extreme changes in the near-Earth environment. We have since built an invisible layer of civilization inside that environment. The electrical wires of 1859 revealed one form of exposure on the ground. Satellites reveal another above it. When people think about GPS, they usually imagine a phone showing a blue dot on a map, a car calculating a route, or a traveller finding a street. But satellite navigation systems do something much broader. Constellations such as GPS transmit carefully timed radio signals from orbit, allowing receivers on Earth to calculate position by comparing when those signals arrive. The same timing capability is also used by many systems that need clocks to remain closely synchronized. Telecommunications networks, parts of financial infrastructure, scientific instruments, transportation systems, and sections of the power sector can use signals from global navigation satellite systems as a source of precise time. This means that space weather does not need to make every navigation satellite stop working in order to matter. It can reduce the accuracy or reliability of the signals passing between satellites and receivers. One important pathway runs through the ionosphere. a region of the upper atmosphere containing electrically charged particles. Radio signals from navigation satellites must travel through this region before reaching receivers on the ground. During strong solar and geomagnetic activity, the ionosphere can become more disturbed and irregular. Those changes can alter how radio signals travel, introducing errors into the measurements used to calculate position. In severe conditions, some receivers may temporarily lose reliable tracking of certain signals or experience larger positioning errors. The effect is not identical everywhere, and it does not mean that every GPS device suddenly gives a completely false location. Accuracy depends on the intensity of the disturbance, the receiver, the signals available, local conditions, and the techniques used to correct ionospheric errors. Modern navigation systems also use multiple satellite constellations, multiple frequencies, ground-based corrections, inertial sensors, and other methods that can improve resilience. The important point is that the atmosphere between a satellite and a receiver is part of the system. A navigation signal does not travel through empty, unchanging space. It crosses an environment that can respond strongly to solar activity. For most of human history, navigation depended on landmarks, memory, stars, coastlines, compasses, and accumulated local knowledge. A disturbance in the ionosphere could not change the position of a mountain or erase a coastline. Modern navigation has gained extraordinary precision by moving part of that function into orbit and into radio signals. The benefit is enormous, but it creates a new dependence on conditions that our ancestors never needed to consider. Timing makes that dependence even less visible. A person may never open a navigation application and still use services whose networks rely on accurate synchronization. Cellular systems must coordinate signals. Digital networks timestamp events. Some financial systems depend on precise clocks to order transactions. Power system monitoring can use synchronized measurements to understand conditions across widely separated locations. Not all of these systems rely on satellite timing in exactly the same way, and many have backup clocks or alternative sources. The temporary degradation of GNSS, therefore, does not automatically cause widespread failure, but it can remove or weaken one of the reference signals that modern infrastructure quietly uses in the background. This is why the phrase GPS outage can be misleading. Space weather may produce a spectrum of effects rather than a simple switch between working and not working. Position accuracy can worsen. Timing quality can degrade. Signals can become harder to track in some regions or for some users. Services with strong backup systems may continue with little noticeable change, while more dependent applications may face greater difficulty. The Carrington Event occurred long before radio navigation or satellites existed, so it cannot tell us directly how modern GNSS would behave in an equivalent storm. What it reveals is the scale of the solar terrestrial environment that modern technology now occupies. In 1859, a geomagnetic disturbance entered telegraph wires. Today, human systems also depend on radio signals traveling from orbit through a dynamic ionosphere. We have placed not only machines but also position and time inside the space weather environment. Radio communication seems almost weightless, because no wire connects the transmitter to the receiver, yet the signal still travels through a physical environment. Some radio systems depend strongly on conditions in Earth's upper atmosphere, especially the ionosphere. This region contains charged particles created partly by solar radiation, and its properties change with time, location, day and night, season, and solar activity. High-frequency radio can use the ionosphere to communicate over long distances because signals can be refracted back toward Earth rather than continuing directly into space. During strong solar events, however, the ionosphere can change rapidly. Intense X-ray and ultraviolet radiation from a solar flare can increase ionization on the sunlit side of Earth and produce strong absorption of some high-frequency radio signals. The result can be degraded communication or, in severe cases, a temporary radio blackout over affected regions and frequencies. Geomagnetic storms can alter the ionosphere in additional ways, sometimes making radio propagation less predictable. These effects do not mean that every radio system fails at once. Different frequencies travel differently, different communication systems use different paths, and many modern networks have alternatives. Satellite communications, ground-based networks, multiple frequency bands, and rerouting procedures can provide resilience when one method becomes unreliable. Aviation is one area where this matters, because aircraft traveling over oceans or high-latitude regions may operate far from dense networks of ground-based communication. High-frequency radio has historically been important for long-range contact in such regions. Space weather can also affect navigation accuracy and increase radiation exposure at high altitude and high latitude during energetic solar particle events. Airlines and aviation authorities can respond by changing communication methods or, when conditions justify it, adjusting routes and altitudes. These are operational responses to a changing environment, not signs that aircraft suddenly become unable to fly. The distinction matters because dramatic descriptions of solar storms often combine every possible effect into one imagined global failure. Real space weather is more selective. A flare can disturb radio propagation through changes in the ionosphere. Energetic particles can create other concerns for spacecraft and high-altitude operations. A geomagnetic storm can affect navigation signals, satellites, and ground infrastructure through different physical mechanisms. These processes may occur during the same period of intense solar activity, but they are not interchangeable. For most of human history, none of this shaped ordinary communication. Our ancestors spoke across short distances, carried messages physically, watched landmarks, and navigated by environmental clues in the sky. The ionosphere was already above them, continuously changing with sunlight and solar activity, but no essential radio link depended on its behavior. The modern world placed communication paths inside that environment. A pilot can speak across great distances because radio waves interact with regions that human senses cannot detect. A ship can know its position from signals arriving from orbit. A phone call may depend on ground networks synchronized by satellite-derived timing. Civilization has gained reach by using parts of the natural environment that earlier generations did not even know existed. That reach brings new forms of dependence, but also new knowledge. Space weather centers can observe solar flares, monitor energetic particles, measure geomagnetic conditions, and issue alerts to industries that may be affected. Communication operators and aviation organizations, therefore, do not face solar activity with the uncertainty of telegraph operators in 1859. They can prepare for some disturbances and switch methods when necessary. The important lesson is not that a future Carrington-scale storm would silence the planet. Science cannot justify such a simple claim. The more realistic possibility is a complicated period of degraded services in which certain radio links become unreliable, navigation accuracy changes, satellite systems experience greater stress, and operators compensate using other technologies and procedures. Some people might notice little. Others working in aviation, communications, navigation, or infrastructure could face significant operational challenges. This unevenness is characteristic of space weather. Its effects depend on geography, technology, timing, and the particular solar event. By extending civilization into radio frequencies and orbital space, humanity created new pathways through which solar activity can matter. The wires of 1859 were only the beginning. Modern communication now travels through an atmosphere and near-Earth environment that are themselves part of the changing Sun-Earth system. A modern Carrington-scale storm would deserve serious attention, but seriousness is not the same as certainty about catastrophe. The physics already gives us several reasons for concern. Strong geomagnetic disturbances can drive currents through long conductors, place unusual stress on parts of electrical grids, interfere with high-frequency radio, disturb satellite operations, and reduce the accuracy or reliability of some navigation and timing services. If several of these effects occurred during the same period, operators across different industries could face difficult conditions at once. That is enough to make extreme space weather a real infrastructure risk without claiming that it would end the modern world. The scale of the consequences would depend on the solar event itself, the magnetic field carried toward Earth, the regions most strongly affected, the state of power networks at the time, the design of vulnerable equipment, and the protective actions taken before and during the storm. A severe event over one geographical area could create a very different outcome from the same level of solar activity interacting with another network. Even within one country, some systems might continue operating normally, while others experience degraded service or temporary outages. Modern infrastructure is not uniform, and neither is space weather. The most scientifically defensible statement is therefore that an extreme geomagnetic storm can create conditions capable of causing major technological disruption. It may threaten parts of the power system, complicate satellite and communication operations, and increase the possibility of cascading problems when dependent services are affected together. What cannot be known in advance from the phrase Carrington scale alone is the exact pattern of damage. This distinction matters because human beings have always lived with hazards whose consequences depend partly on what has been built in their path. A flood crossing an empty valley is not the same social event as a flood crossing a dense city. An earthquake beneath an uninhabited region does not create the same disaster as an earthquake beneath fragile infrastructure. Solar activity follows a similar logic. The natural event is only one side of the risk. Exposure, engineering, preparation, and dependence determine much of what happens next. Our distant ancestors lived beneath an active sun, but had almost no electrical infrastructure for geomagnetic disturbances to enter. People in 1859 had telegraph networks, so the storm disrupted communication and produced unusual electrical effects without collapsing the broader structure of society. We have built far more systems into the same physical environment, which raises the possible consequences, but we have also built scientific monitoring, operational procedures, protective equipment, redundancy, and emergency response. Both changes have to be considered. Ignoring modern dependence would underestimate the risk. Ignoring modern resilience would exaggerate it. This is why an extreme solar storm should not be described as harmless, simply because civilization survived 1859, and it should not be described as an automatic apocalypse simply because modern society uses electricity. The realistic concern lies between those extremes. A sufficiently severe event could produce regional or multi-regional power problems, communication difficulties, satellite anomalies, navigation degradation, and knock-on effects in services that depend on those systems. Some failures might be brief, others could take longer to repair, particularly if specialized equipment were damaged. But the exact duration and geographical extent cannot be read directly from the historical Carrington event because the world of 1859 did not contain the technologies we are trying to evaluate. The event gives us evidence about the power of the Sun-Earth interaction, not a script for the future. It also reminds us that risk is shaped by choices made long before any storm arrives, how networks are designed, how much redundancy exists, how quickly warnings are shared, and how effectively operators can respond. Its warning is therefore conditional rather than prophetic. Extreme space weather can challenge the foundations on which modern life depends. Whether that challenge becomes an inconvenience, a severe regional emergency, or something broader would depend on the interaction between nature and the civilization present when the storm arrives. The most dramatic predictions about a future Carrington-scale storm often begin where the evidence ends. It is possible to describe real physical risks without knowing exactly how a modern event would unfold. What cannot be stated with scientific confidence is that one severe solar storm would automatically end civilization, destroy the entire internet, disable every satellite, or collapse all electrical grids at the same moment. Those outcomes depend on too many variables, and modern infrastructure is too diverse for a single universal prediction. The internet, for example, is not one machine that can be switched off from a single point. It is a collection of data centers, fiber optic cables, routers, terrestrial networks, undersea links, power supplies, satellite connections, and local systems spread across the planet. Some of those components can be affected indirectly if electrical power or communication services are disrupted, while others are relatively insensitive to geomagnetically induced currents themselves. Fiber optic cables carry information using light rather than electrical current through the fiber, although the equipment that powers and manages communication networks still depends on electricity. A major power disturbance could therefore interrupt internet access in affected regions without proving that the entire global network would disappear. The same caution applies to satellites. Space weather can increase radiation hazards, create charging problems, disturb the upper atmosphere, and degrade navigation or communication services, but satellites occupy different orbits and use different designs. Some may experience anomalies while others continue operating. power grids are equally varied. Their response depends on geography, geology, line orientation, transformer design, network configuration, operating conditions, and the actions taken by grid operators. A serious failure in one region cannot simply be copied across every country on Earth. Even neighbouring power systems can differ in how they are grounded, protected, operated, and connected to surrounding networks. So exposure is not equivalent to outcome. The same storm can therefore create very different technical consequences across the map. For most of human history, people face natural hazards with far less scientific knowledge but also far fewer technological dependencies. Modern civilization has increased its exposure by linking essential services to electrical and digital systems, yet it has also increased its ability to observe hazards, communicate warnings, isolate problems, reroute services, and repair damaged infrastructure. Any realistic assessment has to include both sides. Ignoring vulnerability produces false reassurance. Ignoring resilience produces false certainty about catastrophe. Even the phrase Carrington scale contains uncertainty, because the 1859 event was measured with 19th century instruments, not the global satellite and sensor networks available today. Researchers can reconstruct its extraordinary intensity from magnetic observations, auroral records, and technological effects, but they cannot recreate every property of the solar eruption or every detail of its interaction with Earth. Using the event as a benchmark is useful, but treating it as a precisely measured template for a future storm goes beyond the historical evidence. The more responsible question is not whether one solar event is guaranteed to destroy modern society. It is which systems could be stressed, how failures might interact, how long important services could remain disrupted, and how effectively operators and communities could respond. That framing may sound less dramatic, but it produces a clearer picture of risk. Civilization does not exist as a single electrical switch. It is a layered collection of systems, some highly exposed, some protected, some redundant, and some capable of operating temporarily without their normal connections. A severe geomagnetic storm could create major emergencies and substantial economic or technological disruption, especially if several infrastructure problems occurred together. Yet a possibility of serious disruption is not evidence for an inevitable global collapse. The lesson of 1859 is powerful enough without exaggeration. The sun can influence technology on Earth, and modern society has built far more technology into that relationship. What happens during the next extreme event will depend not only on the storm that arrives, but on the systems, preparations, and decisions already waiting beneath it. The most serious modern risk from an extreme geomagnetic storm may not come from one spectacular failure, but from several ordinary failures arriving close enough together to reinforce one another. A power disturbance can affect communication equipment. Communication problems can slow the coordination of repair crews. Transportation difficulties can delay fuel and replacement parts. Water systems may depend on electricity for pumping and treatment, while emergency generators depend on fuel deliveries that require functioning roads, communications, and logistics. None of these links guarantees that the next one will fail, but together they explain why engineers and emergency planners pay attention to cascading effects. Modern infrastructure is built as a network of networks. Electricity supports telecommunications, telecommunications supports control and coordination, digital systems help manage transportation and finance, and all of them depend on people, physical equipment, and supply chains. When one network is disturbed, the others do not automatically collapse. Many have backup systems, redundant routes, the ability to isolate damaged components. The problem becomes more difficult when several backups are required at the same time or for longer than they were designed to operate. A hospital may continue through a local outage using generators. A mobile tower may run on batteries temporarily. A data center may switch to backup power. These are examples of resilience, not fragility. Yet every backup has conditions. Batteries discharge. Generators require fuel and maintenance. Spare components must be transported. Repair teams need information about where damage occurred. If several supporting systems remain under stress, recovery can become slower even when the physical damage is limited. This is the difference between a hazard and a cascade. The hazard may begin with geomagnetic activity, but the social consequences depend on how that disturbance moves through connected human systems. Our ancestors faced cascades of a different kind. A failed harvest could weaken food reserves, which could affect health, migration, trade, and conflict. A flood could destroy a road and isolate communities from supplies. Human societies have always been vulnerable to chains of dependence. What is distinctive about the modern world is the speed and scale with which electrically connected systems can influence one another. A problem in one technical layer can be transmitted into another without anyone seeing the original cause. That does not make collapse inevitable. It makes system design and recovery planning important. A severe geomagnetic storm could, for example, place pressure on parts of a power grid, while satellite navigation becomes less accurate, while some radio links become less reliable. Each effect might be manageable alone. The greater challenge would be handling them together, especially if operators need accurate communication and timing while responding to electrical problems. Even then, the outcome would vary by region and system. Some areas could remain largely unaffected. Others might experience short disruptions. A smaller number could face more serious problems if infrastructure damage, limited redundancy, and difficult recovery conditions happen to overlap. This is why forecasts that jump directly from solar eruption to global civilization failure miss the most useful question. The real issue is not whether everything stops. It is whether enough important systems are disrupted together to make recovery harder than expected. That question can be studied, planned for, and improved through engineering. Redundant communication paths, protected equipment, emergency power, spare components, operational training, and better space weather warnings can reduce the chance that one failure becomes many. The Carrington Event is therefore not a prophecy of a technological ending. It is a reminder that connection changes the shape of risk. The same networks that make modern civilization fast, efficient, and cooperative can also allow disruption to spread across boundaries between systems. The sun supplies the natural disturbance, but the architecture of civilization determines how far its consequences travel. In that sense, the most important vulnerability is not a single transformer, satellite, or radio link. It is the possibility that many systems need one another precisely when several of them are under pressure at the same time. Unlike the observers of 1859, modern societies do not have to wait for telegraph wires, auroras, or unusual instrument readings on the ground before realizing that the sun has become active. A network of spacecraft and solar observatories now watches the sun across wavelengths that human eyes cannot see, while other instruments measure the solar wind and magnetic conditions in space closer to Earth. This monitoring does not allow scientists to prevent a solar eruption, but it changes the amount of information available before its effects arrive. Telescopes can track sunspot regions and detect powerful flares. Instruments can observe coronal mass ejections moving away from the sun and estimate whether an eruption appears likely to travel toward Earth. Spacecraft positioned between Earth and the sun can then sample the solar wind and the magnetic field carried with it before that material reaches the planet. These measurements are especially valuable because the strength of a geomagnetic response depends not only on the speed or size of an arriving disturbance, but also on its magnetic structure. When conditions become favorable for strong interaction with Earth's field, forecasters can update warnings and give infrastructure operators a clearer picture of what may be coming. The process is not perfect. Solar eruptions expand, change, and interact with the surrounding solar wind as they travel. Their direction and arrival time can be estimated with uncertainty, and the magnetic orientation that matters so much for geomagnetic activity is not always known far in advance with the precision operators would prefer. Space weather forecasting therefore resembles other forms of environmental forecasting in one important way. Observation reduces uncertainty, but it does not eliminate it. The difference from 1859 is still enormous. Carrington could record a brilliant flare and wonder whether it had any connection to changes measured on Earth. Telegraph operators could experience abnormal currents without receiving a warning from a global forecasting center. Modern observers can combine images of the sun, measurements in interplanetary space, magnetic data from the ground, and models of Earth's near-space environment into a continuously updated assessment. This represents a major change in the human relationship with the Sunday. For most of our species' history, people learned about environmental danger through direct experience. Dark clouds suggested rain, rising water warned of floods, smoke revealed fire. The sun's magnetic activity offered few comparable signs because the crucial processes were invisible and far away. Only when an aurora appeared, or after electrical technology had been disturbed, did the consequences become obvious. Modern instruments extend human perception far beyond those natural limits. They allow us to detect changes on the sun before our bodies or machines feel their effects. That does not make civilization immune to extreme space weather, but it gives time for decisions. Grid operators can increase awareness and adjust operations when conditions justify it. Satellite operators can delay sensitive procedures or place spacecraft into safer configurations. Aviation and communication services can prepare for possible radio or navigation disturbances. Emergency planners can be alerted that several infrastructure sectors may face unusual conditions at the same time. The usefulness of these actions depends on warning quality, local procedures, and the event itself, and no single response guarantees that damage will be avoided. Still, preparation changes the risk. A natural hazard encountered without information is different from the same hazard observed before arrival. The Carrington Event remains powerful partly because people in 1859 stood near the beginning of electrical civilization, while their ability to observe the Sun-Earth system was still limited. Today, humanity has placed instruments along much of that physical chain. We watch active regions form on the Sun, observe erutions leaving it, measure conditions in the solar wind, monitor Earth's magnetic response, and issue alerts when technological systems may be affected. The Sun has not become quieter because we learned to watch it. What changed is our ability to see the disturbance developing before it reaches the infrastructure we depend on. That knowledge cannot stop an extreme solar event, but it can turn some of the uncertainty that surrounded 1859 into preparation. And preparation is one of the most important differences between the world Carrington knew and the world that would face a comparable storm today. Space weather forecasting begins with a limitation that cannot be engineered away. Humanity cannot stop a coronal mass ejection once it has left the Sunday. There is no practical shield that can be placed between Earth and an eruption moving through interplanetary space, and no technology can turn off the magnetic activity that produces it. Preparation therefore depends on observing the event early enough and understanding its likely path well enough to give vulnerable systems time to respond. When a large eruption is seen leaving the Sun, scientists can estimate its speed, direction, and possible arrival window using images and models. If it appears likely to intersect Earth, alerts can be issued before the strongest geomagnetic effects begin. Those forecasts are useful, but they are not exact schedules. A coronal mass ejection expands as it travels, can interact with slower or faster solar wind, and may change in ways that make its arrival difficult to predict precisely. Even more important, the magnetic orientation carried inside the arriving plasma strongly influences how efficiently it couples with Earth's magnetic field. That property cannot always be determined confidently while the eruption is still far from Earth. Spacecraft positioned upstream in the solar wind can provide a much clearer measurement shortly before the disturbance reaches the magnetosphere. But by then, the remaining warning time may be relatively short. Forecasting therefore happens in stages. Early observations can show that an eruption is coming toward Earth and provide a broad estimate of its arrival. Later measurements can refine the assessment and reveal whether the magnetic conditions are becoming especially favorable for a strong geomagnetic response. This layered warning system is far removed from the experience of 1859. Carrington observed a bright flare but had no instrument capable of following the associated disturbance through space. Telegraph operators learned about the storm only when their own equipment began behaving strangely. Modern operators can receive information before the effects become obvious on the ground. A power company may increase staffing, review vulnerable equipment, adjust operating conditions, or delay maintenance that would otherwise reduce network flexibility. Satellite operators can avoid certain sensitive activities, monitor spacecraft more closely, or prepare for protective responses. Aviation and communication services can watch for expected radio or navigation problems and plan alternatives. These actions do not guarantee that an extreme storm will pass without damage. They reduce uncertainty and create options. Human beings have always benefited from this kind of advance notice. A storm warning does not stop wind from arriving, but it can move people away from danger. A flood forecast does not prevent rain, but it can give communities time to protect equipment and organize response. Space weather forecasting follows the same general principle, even though the hazard is invisible to human senses. Our ancestors could react only after environmental change became visible or physically felt. Modern instruments allow us to respond to processes occurring millions of kilometers away before their consequences fully reach the systems around us. The challenge is that forecasts must communicate uncertainty without becoming uselessly vague or falsely precise. An operator needs enough information to justify protective action, but unnecessary action can also carry costs. Taking equipment offline, changing routes, or altering network operations may reduce efficiency and create other risks. The goal is therefore not to react dramatically to every solar eruption. It is to match the response to the evidence as it improves. This is one of the most important advantages modern civilization has over the world of Carrington. We cannot control the sun, and we cannot know every detail of an extreme event before it arrives. But we can watch the chain unfold from solar eruption to interplanetary space to Earth's magnetic environment, updating decisions as the uncertainty narrows. The natural hazard remains beyond human control. The amount of surprise does not. That difference can matter when infrastructure operators must choose between ordinary operation and temporary protective measures. Forecasting cannot promise safety, but it can convert an invisible approaching disturbance into a problem that people can recognize, discuss, and prepare for before the first technical effects appear. The decades after the Carrington event have given scientists something the people of 1859 did not have: examples of strong space weather interacting with modern technology under direct observation. One of the clearest occurred in March 1989, when a major geomagnetic storm contributed to the collapse of the Hydro-Quebec power grid in Canada. The blackout did not prove that every strong geomagnetic storm will shut down an electrical network, and it did not resemble a global technological collapse. What it demonstrated was more specific and therefore more useful. Geomagnetically induced currents can enter a large power system, interfere with its operation, and help create conditions in which protective equipment and voltage problems lead to a widespread outage. Engineers were able to study the event afterward, examine how the network responded, and improve understanding of how geomagnetic disturbances interact with power infrastructure. Those lessons also encourage better monitoring, operating procedures, and awareness of geomagnetic risk within the power industry. The lesson was not that modern grids are helpless. It was that space weather had moved from an unusual 19th century telegraph problem into the operating reality of an electrical civilization. Another important reminder came in July 2012, when the Sun produced an exceptionally strong eruption directed through a region of space near Earth's orbit at the time. Spacecraft measurements showed that the event was extreme, and researchers have studied it as an example of the kind of solar eruption that could have produced major space weather effects if its trajectory had intersected Earth more directly. Because it missed our planet, it did not become a modern Carrington event on the ground. That near encounter is scientifically valuable because it separates two ideas that are often confused. The Sun can produce an extreme eruption, yet Earth experiences severe consequences only if the event is directed toward us and interacts strongly with our magnetic environment. Solar activity alone is not the whole story. Geometry, timing, magnetic orientation, and the condition of human systems all matter. This perspective also reconnects the problem with the much longer history of our species. For countless generations, powerful solar eruptions may have occurred without leaving any technological record, because there were no electrical networks or satellites available to respond. An aurora might have been seen, but a power grid could not fail because no power grid existed. Modern technology has made some solar events more consequential, but it's also made them easier to detect, measure, compare, and learn from. The 1989 storm left detailed technical evidence from a functioning power network. The 2012 eruption was observed by spacecraft capable of measuring conditions that Carrington could never have seen. Together, these events show why preparedness is based on more than a single episode from 1000 859. Scientists can compare many storms, improve models, study vulnerable equipment, and refine operational procedures. No historical example provides a perfect rehearsal for the future because each solar eruption and each technological network is different. A storm weaker than Carrington can still cause serious regional problems under unfavorable conditions, while an extremely powerful eruption may have little effect on Earth if it misses the planet. This uncertainty is not a reason to ignore the hazard. It is the reason monitoring and resilience matter. The Sun has continued to demonstrate that intense space weather is physically possible, while modern infrastructure has demonstrated that some of its effects can be managed, studied, and reduced. Carrington remains a benchmark because of the extraordinary disturbance recorded in 1859, but it is not our only source of knowledge. Later events have transformed a historical mystery into an engineering problem that can be observed in real time. Humanity cannot choose when the Sun becomes active, and it cannot guarantee that the next extreme eruption will miss Earth. What it can do is learn from every storm that arrives, every near miss that is measured, and every technological failure that reveals where preparation can improve. The lasting importance of the Carrington event is not that it destroyed the world of 1859. It did not. Cities continued functioning, governments remained in place, trains still moved, ships still sailed, and the basic structure of 19th century society survived. What the event revealed was something more fundamental. Activity on the Sun could produce measurable effects in technology resting on the surface of Earth. Telegraph operators saw unwanted currents, sparks, communication failures, and in some cases circuits behaving even after their usual batteries had been disconnected. At the same time, magnetic instruments recorded disturbances and auroras appeared across unusually wide regions. Seen together, these observations showed that the Sun, Earth's magnetic environment, and human electrical systems were not separate worlds. They could become part of one physical chain. That discovery mattered because electrical civilization was only beginning. In 1859, the telegraph was one of the few technologies extensive enough to reveal the connection. Most homes, farms, factories, transportation systems, and essential services were not yet dependent on large electrical networks. The storm therefore encountered a civilization with limited technological exposure. The physical event may have been extreme, but the number of systems available for it to disturb was relatively small. This distinction is what gives the historical record its modern meaning. The Carrington event should not be treated as a failed apocalypse whose danger was hidden only because people were lucky. It should be understood as an early experiment performed unintentionally by nature on a new kind of human infrastructure. The results showed that long conductive systems could respond to geomagnetic change. Everything built afterward expanded the importance of that result. Power transmission networks became larger, radio communication moved information through the upper atmosphere, satellites entered the space environment, navigation and timing became dependent on signals traveling from orbit. Digital networks connected services that once operated separately. None of these developments made technology foolish or civilization inherently fragile. They created extraordinary capability, but they also multiplied the places where the Sun-Earth system could intersect with human engineering. For most of human evolution, solar activity belonged mainly to the environmental background. Our ancestors experienced daylight, seasons, climate, and occasional auroras without possessing machines that could register geomagnetic storms as operational problems. The natural process existed long before electrical civilization, but vulnerability changed as human tools changed. Carrington's generation happened to live at the moment when that transition became visible. Their telegraph wires were simple compared with modern infrastructure, yet those wires were enough to reveal a principle that still applies. A changing magnetic environment can enter human technology through the physical pathways we construct. The historical lesson is therefore neither that technology will fail, nor that extreme space weather is harmless. It is that technological exposure grows from the relationship between natural forces and the systems society chooses to depend upon. Modern monitoring, engineering, redundancy, and emergency planning can reduce that exposure, sometimes substantially. But preparation begins by recognizing that the connection exists. In this sense, the most important thing left by 1859 was not a prediction of destruction, it was evidence. A bright solar event was observed. Earth's magnetic field became violently disturbed. Auroras spread across the sky, and electrical networks behaved in ways their operators had not intended. Those records gave later science a foundation for understanding space weather. They also transformed the Sun from a distant astronomical object into part of the operating environment of technological civilization. The people who watched telegraph needles move strangely could not know how many future systems would depend on electricity, satellites, radio, and precise timing. But the relationship they witnessed has only become more relevant. The event did not end their world. It showed for the first time on a large technological scale that the world humans were beginning to build was connected to the activity of the star above it. That recognition remains more valuable than any dramatic prophecy, because evidence can guide engineering, planning, and resilience without pretending that the future is already known. Modern civilization is powerful, partly because it is connected. Electricity can move across vast regions. Information can cross continents almost instantly. Satellites can coordinate navigation, and digital networks can link hospitals, banks, factories, transportation, and governments. These systems create capabilities that earlier societies did not possess. They also create dependencies that earlier societies did not have to manage. A person living before electrical networks could lose a local tool, a road, or a source of fuel without automatically losing communication, refrigeration, navigation, and access to information at the same time. Modern life often concentrates many functions onto shared infrastructure. When that infrastructure works, the result is efficiency. When it is disrupted, the consequences can spread beyond the original technical problem. This is why the comparison between our ancestors and ourselves should not become a romantic story in which the past was somehow safer or stronger. Earlier humans faced hunger, disease, exposure, violence, drought, and countless other dangers with fewer resources and less scientific knowledge. Their advantage in relation to geomagnetic storms was much narrower. There were simply fewer electrical systems for those storms to disturb. A strong solar event could alter the sky above them without entering a transformer, degrading a navigation signal, or placing a satellite into a difficult operating environment because none of those technologies existed. Modern society has traded that limited exposure for enormous capability. We can move food across long distances, pump water into dense cities, preserve medicine, communicate during emergencies, monitor weather, coordinate transportation, and share scientific information in ways that would have been impossible for most of human history. The price is not that technology makes civilization weak. The price is that connection creates obligations. If many essential services depend on electricity, then protecting the electrical system becomes part of protecting those services. If navigation and timing depend on satellites, then space weather becomes relevant to activities on the ground. If repair crews depend on communication and transportation, then resilience requires more than protecting individual machines. It requires thinking about how systems support one another. This is one of the deeper lessons hidden inside the Carrington Event. The telegraph was valuable because it connected distant communities faster than any messenger could travel. The same wires that created that advantage also created a path through which geomagnetic currents could interfere with communication. The benefit and the vulnerability came from the same physical connection. Modern networks repeat that pattern on a much larger scale. A power grid can share electricity across regions because it is interconnected. A global navigation system can serve millions of users because signals are distributed from orbit. The internet can survive many local failures because information has multiple possible routes, yet local access still depends on powered equipment and functioning networks. Connection can therefore increase resilience in one situation and create dependence in another. There is no contradiction in that. It is a feature of complex systems. For most of our species' existence, survival depended heavily on local knowledge, physical labor, nearby resources, and social cooperation. Modern civilization added technological layers above those ancient foundations. Water still has to move, food still has to reach people, bodies still need shelter, medicine, and communication. What changed is the machinery that now performs or coordinates many of those tasks. A geomagnetic storm matters because it can interact with that machinery, not because the sun suddenly becomes hostile to human life. The real comparison between 1859 and today is therefore not a contest between strong ancestors and fragile descendants. It is a comparison between two different architectures of dependence. The people of Carrington's time had fewer electrical capabilities and fewer electrical exposures. We have far more of both. Our challenge is to keep the benefits of connection while designing enough redundancy, preparation, and flexibility that disruption in one network does not automatically become disruption everywhere else. The price of connection is not inevitable collapse. It is the responsibility to understand what our connections require. The Carrington Event does not ask us to fear the Sunday. It asks us to understand the world we have built beneath it. The sun has always been active, and Earth has always existed inside a changing magnetic environment. Long before cities, power grids, satellites, or radio, our ancestors lived through solar activity without knowing that invisible disturbances were moving through space around them. What changed was not the existence of the hazard, but the number of human systems capable of responding to it. In 1859, that new relationship became visible through telegraph wires, magnetic instruments, and auroras spread unusually far across the sky. Today, the same physical processes intersect with a civilization that depends on electricity, orbital infrastructure, radio communication, precise timing, and networks that coordinate essential services. That dependence makes extreme space weather worth taking seriously. It does not make catastrophe inevitable. The useful response is neither dismissal nor fear, but resilience. Engineers can study how geomagnetically induced currents enter power systems. Satellite operators can design spacecraft for a harsh radiation environment. Navigation and communication providers can build redundancy. Space weather centers can observe eruptions and distribute warnings. Grid operators can prepare procedures for unusual geomagnetic conditions. Emergency planners can examine how electricity, water, communication, transportation, and fuel supply depend on one another. None of these measures can make the sun quiet, but they can change how a natural event becomes a human emergency. This is a pattern that reaches far beyond space weather. Human history is filled with environmental forces that people could not control but gradually learned to understand. Rivers still flood after levees are built. Earthquakes still occur after stronger buildings are designed. Storms still form after forecasting improves. Knowledge does not remove nature from the story. It changes the relationship between exposure and consequence. The same is true here. A future extreme solar storm could create serious disruptions, and some systems could be affected more strongly than others. The exact outcome cannot be known in advance, because it would depend on the properties of the eruption, its interaction with Earth, the geography of the affected regions, the condition of infrastructure, and the decisions made as warnings develop. What can be known is that preparation matters. The lesson left by 1859 is therefore more practical than apocalyptic. Civilization became vulnerable to space weather because civilization became electrically connected, but the same scientific and technological development that created that exposure also gave us tools to recognize it. We can measure magnetic fields that Carrington could only partly infer. We can watch eruptions leave the Sunday. We can place instruments in space, model possible impacts, communicate warnings across continents, and improve systems after every significant storm. Our ancestors possessed fewer technological vulnerabilities because they possessed fewer technological capabilities. We cannot return to their world without also surrendering many of the systems that protect health, move food, supply water, connect families, and preserve knowledge. The question is not whether connection was a mistake. It is how wisely we manage the dependencies that connection creates. Perhaps that is the deepest meaning of the Carrington Event today. A storm observed in the first age of electrical communication became a message for a civilization built almost entirely around networks. The message is not that the modern world is doomed, and not that technology has made humanity helpless. It is that every new layer of connection changes both what we can do and what can affect us. The sun will continue to change according to physics that began long before human beings existed. Our responsibility lies in what we build beneath it, how well we understand those systems, and how carefully we prepare them for forces beyond our control. And that leaves a question larger than any single solar storm. When civilization connects more of the world together, does that connection always make us stronger? Or does every new strength also create vulnerabilities our ancestors never had to face?